Everyone, today I'm going to tell you a little bit about magnetic fields. And to start off, we're going to review some of the basic concepts of magnetism that I'm sure you'll remember. And then we're going to look at how these magnetic fields look like around various different kinds of things that actually produce the magnetic fields. Okay, so to start off, let's start with the basics of the law of magnetism. So this is the one that you've probably heard before. The first thing is that unlike charge, when we talked about charge, you could have a charged object like something as small as a proton, or it could be a charged sphere that has some surface charge density or something, whatever. The idea is that charges can exist as even just a single elementary charge, whether it's positive or negative. However, the magnets don't do this. There's no such thing as a magnetic monopole. You can't just have a north pole sitting around. You always have to have a dipole, where it's a north pole and a south pole, okay? Those two things always show up together. This leads into the law of magnetism, which is that opposite magnetic poles attract, but similar magnetic poles or same magnetic poles repel. So if you see this little graphic here, I have the north pole of the uppermost magnet being attracted to the blue, the south pole of the lower magnet, right? So those are opposite magnetic poles and they attract. Okay, so when we have a magnet, therefore, it will create a magnetic field. Now, we've talked about fields several times already in the context of gravitational fields and electric fields. So it should be no surprise, hopefully, that the magnetic field created in this case is a vector field. And so just like because magnets are always dipoles, we want to draw the vector fields in such a way that we're consistent. So the way that we do that is we decide, let's draw the arrows of the field in a way that the north pole would move. So in this case, you have a bar magnet, and you can see that the arrows come out of the North Pole because, after all, another North Pole would be deflected away. And those arrows come into the South Pole because a North Pole would be attracted to that South Pole, right? It would point towards that South Pole. So if you want to think about another way, it's like, which way would a North Pole point if you were to put it? And again, the idea there is a North Pole would point away from a North Pole, and it would point toward a South Pole. Okay, so you probably know that the Earth has a magnetic field because the Earth itself is basically a gigantic magnet. So that's caused by its rotating iron-nickel core, and the Earth basically creates a large magnetic field around itself. It permeates quite far out into space, I think actually beyond the moon's orbit. We'll talk more about why that's important later, but one thing that's key to understand is that the pole, the magnetic pole that sits in the northern hemisphere of the Earth, is actually a south magnetic pole. And that might seem kind of odd, like why is that? But if you think about it, anytime you have a compass, the compass needle, the north part of the compass needle, right? The compass needle is actually a small magnet. The north pole of the compass needle points towards geographic north. Well, it points towards the magnetic pole, actually. And so if that's the case, if that north pole is pointing towards the Earth's, compass, the Earth's, that is to say, the Earth's magnetic pole, then that means that the pole that exists in the north hemisphere has to be a south magnetic pole. Otherwise, compasses wouldn't work the way they do. So the Earth's magnetosphere, again, this magnetic field that permeates out into space, protects us from cosmic particles. I'll talk about that more on another day. But what you may not realize is that the magnetic poles are actually moving. And so in 2018, I have here that the poles moved about 55 kilometers, which you might think, oh, that's not that far. And, maybe in the grand scale of things, it's not that far, but it's enough that things like the GPS satellite system have to be updated regularly, like at least once a week, because if they didn't take into account fluctuations in the magnetic field, and they would actually give you wrong directions. Okay, so one of the theories of how magnets work actually goes back to an understanding of atoms, really, if you carry this through all the way through. But to break things down a little bit, there's this thing called the domain theory of magnetism, or the domain theory of magnets. And so the idea is that if you have a ferromagnetic substance, that word ferromagnetic means that it's ferro means iron, and magnetic, of course, is magnetic. So the idea is that you have an iron magnet, or something that's at least partially iron. Then that substance, if you were to look at it under a microscope, well, not really, but if you imagine looking at it under a microscope, you would see tiny little magnets. Now, again, you don't actually see this, but you can actually see some structures in the substance under maybe some kind of electron microscope, where you would basically be able to see something called the domains. The grains rather of the substance, and that kind of goes along with domains, but that's a whole nother story. Anyway, so if you were to imagine breaking up a substance into smaller and smaller pieces, those little pieces, those domains, are actually small magnets, tiny magnets. And each of those tiny magnets, of course, has a north and south pole, because we don't have monopoles. And in normal circumstances, if you just have a chunk of iron, those domains will be pointed in all sorts of different directions. The only way to actually turn a chunk of iron into a magnet, well, actually there are a couple of ways, but one easy way is to take another permanent magnet and just rub it in the same direction each and every time, and that will then slowly get the domains to align. And so you'll eventually create a permanent magnet that way. You can also temporarily align the domains with an external electric field. So something like an electromagnet, which is a coil of wire. We'll talk about that shortly. And this is actually one of the best and easiest ways of creating a very strong magnet, is to basically combine a chunk of iron, let's say, with an electric field, right, coming from an electromagnet. So we'll talk about that in a second. You can break the alignment in a couple different ways. If you heat up a magnet, then again, those domains will start moving out of alignment with each other. You can bang it. You can rub it in a different way, potentially with a permanent magnet, and so that will, again, cause those domains to misalign or de-align. Okay, so if we talk about, so one thing that's important to understand about magnetism and electricity is that these two things are not actually as separate as they might seem to be. So a person who's often credited with discovering this is Hans Christian Ørsted, and he basically showed that if you ran a current through a wire, then a magnet nearby, like let's say again a compass, would deflect. So in other words, we have a wire with a current passing through it, and then all of a sudden a magnet that was nearby would actually deflect, as if there were a magnetic field there. How does that work? Well, so it turns out that Ørsted gives us this principle of electromagnetism, that once you have moving electric charges, meaning charges through a conductor, for example, then those moving electric charges produce a magnetic field. Okay, so that was basically the understanding of the observation. And these field lines are determined with the right-hand rule. Now, I'll go over the right-hand rule shortly, but again, to use the right-hand rule, you need to have your right hand. I'm afraid I may be mirrored in this video, but this is my right hand. Okay, so again, if you're going to do this, make sure that you know which is your right hand. Anyway, okay, so let's talk about some common geometries for magnets. So the basic one, if we're going to look at Ørsted's discovery anyway, the basic one is just a straight conductor. So in this case, the gray cylinder that you're seeing there is the wire, and the red arrow with the eye, that indicates the electric current. Okay, so I'm going to use this for my conductor. It's just a brush, but that's fine. So in this case, if this were my wire, this were my straight conductor, and I had the current going this way, then I'm going to take my right hand and point my thumb in the direction of the current, just like that, okay? And then my fingers will curl around the brush like this, and that will tell me the direction of the magnetic field. Okay, so it doesn't really matter which way I orient the wire. Always my thumb goes in the direction of the current and my fingers curl around just like that. Now, if I have a loop, a conducting loop, then essentially this works the same way, except that at each point along the loop, I put my thumb. And so again, my thumb will go in the direction of the current, and my fingers will curl in the direction of the magnetic field, right? Again, the way that the magnetic field is pointing. And so if you can see that loop there, by following the current along the loop, then in this case, my fingers would always point towards my face. So in other words, in the case of a loop like this, then the magnetic field would point towards me, right, in that case. Now, if you kind of combine these two together, or rather, I should say, if you make a whole bunch of loops, then you produce what's called a solenoid, which is basically one long coiled conductor. And so really, this is just a loop, but multiplied out many times. And so the concept is the same there, just like for a single loop, if you have, you would have the magnetic field lines going through. If you have a whole bunch of loops or a solenoid, then again, you have the magnetic field going through like so. But in this case, what you normally do to show which way to figure out which way the magnetic field is going is you kind of turn things around. You basically coil your fingers along the direction of the current. So this is why it's sort of similar to the first situation, sort of. You coil your fingers in the direction of the current, and then your thumb points in the direction of the magnetic field lines, okay? So it's a little bit different. It's kind of like the first two situations put together, but again, it's different in that the first two situations, your fingers point in the directions of the magnetic field and your thumb points in the direction of the current. In the solenoid, it turns around, right? Your fingers point in the direction of the current, right? Curling through the solenoid, and your thumb points in the direction of the magnetic field. So one thing you might like to do is try and figure out, well, hey, how can I make a stronger electromagnet using a solenoid? So one thing to keep in mind is that a solenoid by itself is just a collection of, it's just a wire, a coiled wire. So in that case, you can say, okay, well, maybe I can increase the current, and that turns out to increase the magnetic field. Or I could increase the number of loops, and that turns out to increase the magnetic field. But there's one other thing to consider, and that's the thing that's inside of the coils. So in that case, that's known as the core. So if you just have a wire which is basically around nothing, then that is an air core. So that's kind of like the base case scenario, an air core. But there's no reason why you couldn't stick something into there. And so what can be done, or what is often done, is you put in a piece of soft iron. And so in that case, you can actually dramatically increase your field strength, your magnetic field strength, approximately by an order of 6,000. Okay, so that's it for this lesson on magnetic fields. I hope that was clear, at least somewhat. I had to play a little bit with my demo there, but hopefully that makes sense. Again, for the right-hand rule, remember that this is my right hand, right? Even though to you this might look like my right hand, I'm not totally sure. But remember, this is my right hand. Always use your right hand when applying the right-hand rule. Okay, thanks very much, folks. I'll see you next time.